Welcome back. Let's learn about osculating circles and planes. Alright, so at any point along a curve, such as this point right here, there will be a circle that fits the curve best. And by the word best, I mean that the circle just barely touches the curve at that point. And the word that we use to describe this in math is osculate, or it translates to the word kiss. So the circle in question here would kiss the curve at that point. Alright, and so we would call the circle that does that not the kissing circle, because that kind of sounds weird, but rather the osculating circle. Or sometimes you might also hear it referred to as the circle of curvature, but I'm going to call it the osculating circle in this video. Alright, so for our curve here at this point, the osculating circle might look like this. It's a circle that just barely touches that point along the curve, and so it would be the osculating circle. Now keep in mind this is just a sketch. This might not be a perfect representation of what the osculating circle would look like at this point along this curve. This is just a random curve that I drew. I don't know what the equation is for it, but hopefully you get the idea that this circle is just barely touching that point along the curve. Alright, but now a couple important things to realize about an osculating circle, such as this one, is that it will share the same unit tangent vector with the point that it is osculating. Alright, so at that point, we would have a unit tangent vector that looks something like this. You would have a vector tangent to that point along the curve. That unit tangent vector is pointing in the direction of the heading of the curve at that particular moment in time. The osculating circle at that point will share the same unit tangent vector. Right, that vector would also be tangent to this point along the circle. Not only that, but the osculating circle will also share the curvature k with that point along the curve. So whatever the value of the curvature is at that point along the curve, the circle itself will have that same value of curvature. And remember, circles have a constant curvature. The curvature remains the same the whole way around a circle. So whatever the curvature is at that point determines that constant curvature for the osculating circle. All right, and then one more thing. For the osculating circle, the unit normal vector at the point will point through the center of the circle. All right, so in this case, the unit normal vector might look something like this. It's perpendicular to the unit tangent vector, right? This would be a right angle right there. And the unit normal is pointing right through the center of the circle. We would say that the center is somewhere about right here. And even if it doesn't cross through, because it would have a magnitude of 1, most likely it's not actually going to cross through the center, but it would still point through it. So even if it wasn't this long, the vector itself would be pointing to the center of the osculating circle. Okay, so those are some key features about an osculating circle at a point along a curve. Now, to help us identify these circles from the perspective of the point that it osculates, what we do is we find the radius of this circle. And recall from our lesson on curvature that the curvature of a circle is equal to just 1 divided by its radius, right? We found this formula in one of our examples that the curvature of a circle is equal to 1 divided by its radius r. All right, that is its constant curvature. Whatever the radius is, 1 divided by that radius is the constant curvature for the circle. And so what we're going to do is actually use that radius to help us identify these osculating circles at points along a curve. And so what we'll do is solve for r, the radius in this equation, and we get the following formula. We call this the radius of curvature. R is equal to 1 divided by k, the curvature. All right, we just solved for r in this equation, and we get this. So whatever the curvature is at a point along a curve, you can take 1 divided by that curvature, and you will find the radius of the osculating circle at that point along the curve. Okay, and so that's very important to remember. Most likely, when working with osculating circles, your task will be to find the radius of curvature of that circle for a particular point. So this is a formula you definitely want to know. And now that's pretty much everything you need to know about osculating circles, but something else that we might be interested in that is related to the osculating circle is what we call an osculating plane. And what an osculating plane is a plane that contains an osculating circle. Alright, so remember, a circle is a two-dimensional shape, so even if you're working within 3D space, I know we're working in 2 dimensions in this graph here, but even if you had a curve in 3D space, an osculating circle at a point along that space curve would still be a 2D shape that would be contained within a plane. Alright, now in our picture here, that plane might look something like this. Obviously, it would extend in all directions forever, but I just have a small section of it drawn here to help you get an idea of what I'm talking about. An osculating plane is just a plane that would contain an osculating circle at a point along a curve. And so something interesting to note about an osculating plane is that it contains both the unit tangent vector and the unit normal vector for that point along the curve that the osculating circle is touching. And so if we want to find an equation of an osculating plane, we can use that knowledge to our advantage. Because remember, in order to find the equation of a plane, we need two things. We need the coordinates of a point in the plane, and we need a vector that is perpendicular or orthogonal to that plane. Now, in the past, when we first introduced planes in 3D space, we referred to that vector as the normal vector. But be careful here, that is not the same as the unit normal vector. Alright, in this case, the unit normal vector is contained within the plane. The normal vector that we use to identify a plane or to create the equation of a plane is not the unit normal vector. It's going to be a different vector. It has to be a vector that is perpendicular to that plane, and therefore it would also be perpendicular to any vectors contained within that plane. And so the vector that we would use to create the equation of the plane would have to be perpendicular to both the unit tangent vector and the unit normal vector. And thankfully, we already know of such a vector, right? We have already defined a vector that is perpendicular to both the unit tangent and the unit normal. It is the unit binormal vector b from our TNB frames that we learned about in the previous lesson. Okay, so in this case, you can imagine that the unit binormal vector would be pointing into the screen. So I'm going to draw it like this. It would look something like that. That's the unit binormal vector b. It would be perpendicular to both the unit tangent and the unit normal vectors. And so as a result, that unit binormal vector is perpendicular or orthogonal to the osculating plane. So it would be the normal vector that we would use to find an equation of that plane. Okay, so the bottom line here is that to find the equation of an osculating plane for an osculating circle at a point along a curve, you want to use that point of oscillation and the orthogonal vector b, the unit binormal vector, in the standard equation for a plane. And so if you don't remember what that looks like, here it is. This is what we used to set up the equation of a plane in the past in Calculus 3. A, B, and C are the components of the normal vector, which in this case would be the components of the unit binormal vector, and x1, y1, z1 are the coordinates of the point in the plane. So in this case, they would be the coordinates of the point of oscillation, that point that the osculating circle touches. Okay, so that is how we can find an osculating plane, the plane that would contain an osculating circle. However, there is one more thing that we might also be interested in finding, which is something that we call the normal plane. And we define a normal plane to be the plane that would cut through the osculating circle. It would also be the plane that contains all of the vectors perpendicular to the unit tangent vector. All right, so that would mean all vectors that are parallel to both the unit binormal and the unit normal vector. So in our sketch here, the normal plane would look something like this. This might be hard to visualize, but if you can imagine, this plane that we're calling the normal plane cuts through the center of the osculating circle, or in other words, it rides along the unit normal vector, and so therefore would contain the unit normal as well as the unit binormal vectors. Okay, so really, not only does it cut through the osculating circle, but it also cuts through the osculating plane. And so as a result, if we were to look at these two planes from the top down, what we should find is that the two planes are perpendicular. The osculating plane and the normal plane at a point along a curve will be perpendicular planes. Okay, and if we want to find the equation of a normal plane, what we have to remember is that it does contain both the unit normal vector and the unit binormal vector, which means that the unit tangent vector is perpendicular to the normal plane, So the normal vector that we would use to create the equation of a plane in this case would be the unit tangent vector. That is a vector that is orthogonal or perpendicular to the normal plane. So using the point of osculation along with that unit tangent vector, we can find the equation of a normal plane using the standard equation of a plane. And so here is that equation once again. The values of a, b, and c correspond to the x, y, and z components of the normal vector, which in this case is the unit tangent vector, and x1, y1, z1 correspond to the x, y, and z coordinates of the point of osculation. Okay, so for both planes, the osculating plane and the normal plane, to find their equations, you're going to use this formula and you're going to use the same point, the point of osculation. What differs is the normal vector, or the vector that's orthogonal to that plane. For the osculating plane, it's the unit binormal, but for the normal plane, it's the unit tangent. Okay, and so with that, that is everything that we might want to find at a point as it relates to an osculating circle. And so what I want to do to end this lesson is take a look at an example problem where we will have a vector function and we are interested in finding the radius of curvature for an osculating circle, an equation of the osculating plane, and an equation of the normal plane at a specific value of t, or at a specific point along the curve. Okay, so let's take a look at that example now. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful, then I'd like to invite you to join my membership site, JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. So if you are interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Alright, so here's our example. We want to find the radius of curvature for the osculating circle, the equation of the osculating plane, and the equation of the normal plane at t equals pi. And our vector function r of t is equal to ti plus sine tj plus cosine tk. Okay, so now unfortunately these problems involve a lot of work, because if you remember, in order to find the equation of the osculating and normal plane, we need to know the vectors from a TMB frame. At the very least, we need to know our unit tangent vector and unit binormal vector, but in order to find the unit binormal, you also have to know the unit normal. So we can't get out of any work here. We're going to have to start these problems by finding the vectors of a TMB frame. And so to start, we need to find the unit tangent vector, and remember that the unit tangent is equal to the derivative of the vector function divided by its magnitude. So we'll start by taking the derivative of our vector function. R prime of t is equal to the derivative of these components. The derivative of t is 1, derivative of sine is cosine, and the derivative of cosine is a negative sine. So we get I plus cosine t j minus sine t k. All right, so now the magnitude of r prime of t, that's what we need next. We'll take the square root of the sum of the components squared. So we have 1 squared plus cosine squared t, and then negative sine t squared will be positive sine squared t. Now, we can simplify this using the Pythagorean identity for sine and cosine. Cosine squared t plus sine squared t is 1. So we have the square root of 1 plus 1. So that's what this becomes, which is equal to the square root of 2. Okay, so the unit tangent vector here, if we put everything together that we've just found, we will have this vector, the derivative of our vector function, divided by its magnitude, but I'm just going to write it like this. We'll have 1 divided by the square root of 2 multiplied by that vector. All right, that's the same as dividing by the square root of 2. So we're multiplying it by I plus cosine t j minus sine t k. All right, so now we have the unit tangent vector. Next, we need the unit normal vector. And remember that the unit normal vector n of t is equal to the derivative of the unit tangent vector divided by its magnitude. So that's what we have to do next. We need to first take the derivative of our unit tangent vector. So let's do that here. T prime of t is equal to 1 divided by the square root of 2 multiplied by the derivative of this vector. All right, the derivative of 1, a constant, is 0. So the x component is just 0, so we don't need to write that. But then for the y component, or the j term, the derivative of cosine is the negative sign. So we have negative sine t j, and then the derivative of sine is cosine, so we still have minus cosine t k. All right, so now we need to calculate the magnitude of this derivative. However, at this point, we really don't need to work in terms of t anymore because we are working at a specific value of t, right? T equals pi. That's where we want to find the equation of the osculating plane and normal plane. So we're not going to be using the general TMB vectors for that. Rather, we want the specific vectors of the TMB frame at t equals pi. So at this point, we don't need to work in terms of t anymore. We just needed to work in terms of t until we took the derivative of the unit tangent, and then we can find the unit normal as well as the unit binormal at t equals pi. All right, so really what we're going to do here is find n of pi. So I'm just going to erase all of those t's and replace them with pi. So we have n of pi, t prime of pi, and the magnitude of t prime of pi. All right, so what I'm going to do is first plug in pi into this derivative and then calculate the magnitude of the resulting vector. All right, so t prime of pi is equal to 1 divided by the square root of 2 times negative sine t times j. If you plug in pi for t, sine of pi is 0, so the whole y component is gone. But then cosine of pi is negative 1. So we have negative 1, but then it's being negated, so it becomes positive 1. All right, so we just have 1 as the z component, so we're just left with k. So we have 1 divided by the square root of 2 times k. We don't really need that parenthesis. We can just write it like that. And so calculating the magnitude then is pretty simple. The magnitude of t prime of pi is going to be equal to the square root of the sum of the components squared, but there's only one component. So we're going to be squaring it and then immediately taking the square root. So we're going to end up with the same value in this case. We have the square root of 1 divided by the square root of 2 squared, which equals 1 divided by the square root of 2. All right, and so then n of pi, or the unit normal vector evaluated at pi, can be found by taking t prime of pi, which is this vector right here, and dividing it by its magnitude. And that's going to simplify very nicely because we're going to have 1 divided by the square root of 2 k divided by 1 divided by the square root of 2. So those two constant multiples cancel out. 1 divided by the square root of 2 divided by itself is 1. So the unit normal vector at pi is just equal to k. That's pretty nice. All right, so now we have the unit normal at pi, and next we probably want to find the unit binormal at pi, but in order to find that, we do need to know what the unit tangent is evaluated at pi. So we have to do that yet, right? Because vector b, or the unit binormal at pi, would be equal to the cross product of the unit tangent evaluated at pi with the unit normal evaluated at pi. All right, so we have to know both of those vectors in order to find the unit binormal. So let's plug in pi into our unit tangent. If we do that, t of pi will be equal to 1 divided by the square root of 2 times this vector, but evaluated at pi. The x component is just 1, so that doesn't change. We're multiplying by I plus cosine of t, which is pi, and cosine of pi is negative 1. So really, instead of plus that term, we have minus j, and then negative sine t, sine of pi is 0, so the whole z component is gone. We just have I minus j. All right, now we have both the unit tangent and the unit normal evaluated at pi. Now we can calculate the unit binormal evaluated at pi. So let's set up the 3 by 3 matrix for calculating the cross product. We're going to have I, j, and k. The middle row will be the components of the unit tangent, and the bottom row will be the components of the unit normal. Now, before I do anything here, to make things easier for ourselves, instead of multiplying 1 divided by the square root of 2 through this vector, and then using those components in the cross product, what I'm going to do instead is use a property of the cross product, which is that you can pull a scalar multiple out from one of the vectors in a cross product and then just multiply it by the result of the cross product using the components of the vector that does not include that scalar multiple. All right, so we can just pull that 1 divided by the square root of 2 out to the outside and then use components of 1, -1 for x and y in the unit tangent. All right, so in our matrix here, we have 1, -1, and 0 as the components of the unit tangent vector. Then for the unit normal, we just have a k term, so I and j are 0, but then k is 1. All right, so we have a pretty nice setup here for calculating a cross product. Now let's actually do it. I'll start by covering up the I column, then calculate a 2 by 2 determinant. -1 times 1 is -1 minus 0 times 0, which is 0. So we get -1 times I, or just negative I. Then you want to subtract the j term. And so covering up the j column, we have 1 times 1 minus 0 times 0. And so you just get 1j. And so I'll write that down here. But don't forget to subtract it. That's just how the cross product formula works. And then for the k term, you want to cover up the k column and then calculate another 2 by 2 determinant. 1 times 0 is 0, minus -1 times 0. That's also 0, so the whole thing is 0. You could write plus 0k, but there's no point in doing that. I'm just going to erase it. Okay, so that right there is the unit binormal vector. One thing I will do, just to make it a little bit nicer, is pull out the common factor of -1 from these two terms. So what I'll say is that vector b of pi is equal to -1 divided by the square root of 2 times I plus j. All right, that just looks a little bit nicer, and it might be easier to use later on. But now we're done. We now have the unit tangent, the unit normal, and the unit binormal vectors at t equals pi for this vector function, or for our curve. So now that we have those, we can finally start doing the new stuff in this lesson, which is to find the radius of curvature for the osculating circle, the equation of the osculating plane, and the equation of the normal plane at that value of t. All right, and the first thing I'm going to work on here is the radius of curvature. Remember that the radius of curvature for the osculating circle looks like this. The radius of curvature r is equal to 1 divided by the curvature k. So in order to find this radius, we have to know what the curvature is at the point t equals pi. And so let's work on that here. We actually have all the information we need now to calculate the curvature. Remember that the curvature k is equal to the magnitude of the derivative of the unit tangent vector divided by the magnitude of r prime of t, the derivative of the original vector function. Now in this case, we want the specific curvature at t equals pi, so we don't want the general magnitudes here. We want t prime of pi and r prime of pi, or at least the magnitudes of those vectors, okay? And we have both of them right here. The magnitude of t prime of pi is 1 divided by the square root of 2, and the magnitude of r prime of pi, while we didn't specifically calculate that, the magnitude of r prime of t is constant. It's always the square root of 2. There's no t's in that expression. So r prime of pi, the magnitude of that vector, will be the square root of 2. All right, so here's our curvature calculation. Curvature will be equal to 1 divided by the square root of 2 divided by the square root of 2. So simplifying, that looks like this. We have 1 divided by the square root of 2 multiplied by itself, which is equal to 1/2. So the curvature is 1/2, which means that the radius of curvature for the osculating circle would be 1 divided by 1/2. All right, so r is equal to 1 divided by 1/2, which is equal to 2. All right, so the radius of curvature is 2. That is the first answer to this problem. The radius of curvature for the osculating circle is 2. Now let's work on the equation of the osculating plane and the normal plane at that value of t. And let's start with the osculating plane. Remember what we need to find the equation of a plane. We need a point in that plane, and we need a normal vector, or a vector perpendicular to that plane. For the osculating plane, the perpendicular vector is the unit binormal vector. All right, so for the osculating plane, we need the point and the vector b. All right, in this case, vector b evaluated at pi. So the only thing we're missing here is our point. We need the specific coordinates x, y, and z. of the point where t equals pi. So to find that, what you want to do is plug pi into the original vector function. That will give you the vector that points to that point along the curve. And so the components of that vector are the coordinates of the terminal point of the vector, which would be the point that we're interested in here. All right, so r of pi is equal to pi times I, right? We have t times I, so that becomes pi. Sine of pi is 0, so the j term is 0. We have 0j. And then cosine of pi is -1, so we have minus k. So that gives us the point pi, 0, -1. All right, those are just the components of our vector translated into the point that it's pointing to. All right, so now to set up the equation of the osculating plane, we have everything we need. We have the point and we have the normal vector, which in this case is the unit binormal. So let's set it up. Remember that the standard equation of a plane is the x component of the normal vector times x minus the x coordinate of the point plus the y component of the normal vector times y minus the y coordinate of the point plus the z component of the normal vector times z minus the z coordinate of the point, and that's all equal to 0. Okay, now if you wanted to, you could choose to use the unit binormal with components of -1 divided by the square root of 2, right? That would be multiplied by both I and j, so that would be the x and y components. However, remember that scalar multiples of vectors are parallel, so there's a lot of different vectors that would be perpendicular to the osculating plane. All of those vectors would be parallel to the unit binormal that we found right here. So really, we don't have to use this specific vector. We can just use a vector parallel to it, which could be a vector that doesn't include that scalar multiple, because scalar multiples of vectors are parallel, all right? So we don't have to include that. We can just use the components of 1, 1, 0, all right? 1 and 1 for x and y, and 0 for z. That will make things a little bit easier for ourselves here. So we have 1 multiplied by x minus the x coordinate, which is pi. So we have x minus pi plus b, which is just 1. And we're multiplying by y minus y1, or the y coordinate, which is 0. And then we have plus c, which would be 0. There is no z component for this vector, and so we would then be multiplying by z minus -1, but that doesn't really matter. That whole thing just becomes 0. And then over here, simplifying, we have 1 times x minus pi, so that's just going to be x minus pi, and then we have 1 times y, all right? Y minus 0 is just y. So here's what we get. We have x minus pi plus y equals 0. And so then just to make it look a little bit nicer, I'll add the constant of pi over to the other side, right? If you add pi to both sides, that will cancel out with this negative pi, giving us the equation of the osculating plane, which is x plus y equals pi. All right, so that is the equation of the osculating plane. Now let's find the equation of the normal plane. For this, we need that same point, but a different normal vector. In this case, a vector perpendicular to the normal plane, remember, is the unit tangent. All right, so we need point and the unit tangent at pi. All right, and we have everything we need. The point is right here, and the unit tangent is right here. Once again, we don't have to use this specific vector. We can use a vector parallel to it because it'll still be perpendicular or normal to the plane. And so we can ignore this scalar multiple and just work with these two nice components. And by the way, if you did use these components multiplied by this scalar multiple and put them into this equation, you will still get the same equation because you'll have a common factor that can be canceled out. So you will get the same thing I got here if you choose to use the exact same vector for the unit binormal, not one parallel to it. Okay, same thing for the unit tangent here when finding the normal plane. You could use this specific vector, but I'm just going to use one that's a little bit nicer to make my work easier. All right, so let's set that up. Let's set up the equation for the normal plane. I'm going to do it right up here. I'm not going to rewrite the standard form for the equation of a plane. I'm just going to use the equation right away. So the x component of our normal vector, which in this case is a unit tangent vector, I'm going to choose to ignore the scalar multiple because we would still be using a parallel vector to the unit tangent. The x component is 1, so we have 1 times x minus the x coordinate, of our point, which is still pi, that comes from right here. And then we have plus the y component from our vector, which in this case will be -1. So really we're going to be subtracting. So we have -1 times y minus the y coordinate of our point, which is 0. So we have y minus 0, and then plus the z component, which is 0. There is no z component. So I'm not even going to bother to write the rest of that term because it's all going to become 0. We have 0, and then this equation is equal to 0. All right, now simplifying, we'll get x minus pi minus y equals 0, right? -1 times y, negative y. And then adding pi to both sides of the equation gives us x minus y equals pi. And there you have it. That right there is the equation of the normal plane at t equals pi for this vector function. All right, and so now we have found everything we set out to find. We found the radius of curvature for the osculating circle. We found the equation of the osculating plane and the equation of the normal plane, all at that value of t equals pi. Okay, but with that, that is it for this example. But if you do want to get some more practice, feel free to check out my examples video that I'll have linked here on the screen. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.